Goldman Sachs estimates that a single technology will add $7 trillion to the global GDP over the next decade. Realizing that growth requires a massive expansion of computational infrastructure. For years, artificial intelligence operated as a sorting mechanism. We call this discriminative AI. If you feed it a dataset, it analyzes the information to categorize it into predefined labels, like identifying whether an image contains a cat or a dog. Generative AI abandons the sorting bins. This architecture learns the underlying statistical patterns of a dataset to produce completely new, non-existent outputs. This shift toward autonomous synthesis allows the technology to automate complex knowledge work across finance, medicine, and software engineering. But that $7 trillion economic projection rests on a paradox. The system relies on highly complex engineering, yet it is entirely dependent on trillions of data points scraped from the internet without compensation. The first major architectural leap in synthetic media creation arrived with Generative Adversarial Networks, or GANs. A GAN is a type of machine learning framework that pits two neural networks against each other to generate realistic data. One network, the generator, constructs a digital forgery. The second network, the discriminator, attempts to flag it as fake. They lock into a continuous feedback loop, repeating the process until the generated pattern matches a target data distribution. While GANs are powerful, recent breakthroughs in highly realistic image generation rely on diffusion models. A diffusion model is a system that learns to create images by destroying training data with random noise and then practicing how to recover it. This relies on a process called iterative denoising, where an AI is trained to incrementally remove static from a heavily degraded image. The model looks at pure static and reverses the noise addition step by step. It hallucinates a highly detailed, coherent image out of total chaos. By pairing this image generation technique with large language models, users can use text prompts to guide the math and summon novel visuals on demand. These models create high-value outputs, not through human imagination, but through advanced statistical probability and noise reduction. To understand how these systems process text, we look at the transformer architecture, introduced in 2017. The transformer is a neural network design that processes sequential data simultaneously, allowing AI to ingest internet-scale volumes of text. Older language models read text word by word. Transformers use a mechanism called self-attention. Self-attention is a mathematical process that weighs the contextual importance of different words in a sequence simultaneously, mapping the relationships between words regardless of their distance in a sentence. Here is where the engineering hits a wall. Developers build the network architecture and feed it the training data, but they cannot fully map how the AI makes its internal decisions. This is the black box problem. A modern language model operates on trillions of parameters. Parameters are the internal variables and connection weights the model uses to make predictions. The interactions between these parameters are so complex that the resulting intelligence can be observed, but it cannot be reverse engineered. We are deploying a technology capable of reshaping the global economy, yet its own creators cannot explain the underlying reasoning behind its outputs. Every generative model shares one absolute requirement: massive oceans of training data. Running these models requires an immense physical hardware footprint of server racks to store and process the information. This training data does not materialize out of thin air. It is the collective, scraped output of human history, art, and labor. Ingesting that material has triggered legal friction. The U.S. Copyright Office is currently investigating the boundaries of authorship and infringement regarding AI training. Developers offer a straightforward legal defense. They argue that AI models learn abstract patterns from data, exactly like a human student, which they claim qualifies as fair use. Critics counter that generative AI is functionally a massive compression engine. They argue the software memorizes protected works and regurgitates them to compete with the original creators in the open market. This chart shows the number of peer-reviewed articles published on the ethics of generative AI across various academic fields. The ethical friction is widespread, with a high concentration of research coming from medicine and the social sciences. The true challenge of this shift lies in learning how to collaborate with a machine that thinks in ways we cannot fully decipher. Generative AI forces us to draw new lines. We are currently redefining the legal and philosophical boundaries of authorship, ownership and the nature of creativity.